This video lecture will again build out of the results we showed in our lecture on statistical decision theory to describe a popular and often effective approach to classification known as naive Bayes. Let's consider why we would use an approach with a name like naive Bayes. Well, to understand this, a lot of times we have a likelihood function that is multidimensional and very difficult to estimate. And naive Bayes gets around this by making a strong assumption. It assumes statistical independence among the features, even when it's clear that they're not statistically independent. So, for example, suppose the likelihood is this one that we talked about in our last lecture, a multivariate Gaussian, and it has dimensionality m. And it has these two parameters. It has the mean vector and it has the variance-covariance matrix, both of which need to be estimated. The parameter estimation for this then is of order m squared because of the variance-covariance matrix. That's what's giving us the grief here because there's a lot of parameters to estimate, order m squared of them. And the complexity of parameter estimation can be even worse with other joint distributions. So if we decide we want to use different joint distributions and put them together, which often we do, then the estimation problem can get very difficult. This is an important principle in machine learning in general, which is why I've highlighted it. And it says that suboptimal approaches with good parameter estimates are better than optimal approaches with bad parameter estimates. So the idea here then is, look, we know we're going to be suboptimal with this naive Bayes approach, but if we can get good estimates for the parameters, then we're probably going to do better in the world of classification and even regression than we would if we really tried to force fit optimal approaches and we don't get very good estimates for our parameters. Okay, so what is the naive Bayes classifier? Well, we start with this notion of the likelihood function, which is this f of x given gi. So this is the likelihood of the data, again, given by this x, which describes the data that we have in our problem. And we have some classification, we have some label. Again, it could be the admission decision, it could be a classification of disease, whatever it is, we've got a label. But we know that within that group, let's say the admitted student group or the patients that have the common cold, there's a set of conditions that we observe, the feature values that we observe which go into those x's. If we assume independence among each one of those features, then we don't have to worry about estimating that variance-covariance function. It's very simple for us to just go forward with a straightforward product form as shown for the likelihood. And this makes the problem much easier for us to estimate than it is if we have to fully estimate even a relatively simple distribution like a multivariate normal. Okay, so we estimate or assume the form for each one of the individual parameters. The nice thing about this is it is a very generalized approach, so we can have a variety of different features that are going to go into the problem. And the features, frankly, can be continuous features, discrete features. We can put them together under this naive Bayes formulation and get a good answer. One way to do the estimation is just to assume each of the class conditional densities is Gaussian. That's a simple way to do it. We can also use a kernel approach, an estimation approach that you've seen in your statistics class, or a mixture model, which is something we'll talk about later in this class. You can also handle these categorical variables using Bernoulli or multinomial estimates, and you can mix them up. Now, we're not going to describe this mixing process here, but I encourage you to think about how you can do that. And frankly, this is what gives naive Bayes its power, is that it can be used in with a variety of different features, with a variety of different forms, and it can work pretty well. The ones that exist for naive Bayes, the software that exists for naive Bayes, for instance in scikit-learn, those basically come pre-ready to go with Gaussians or Bernoullis or multinomials. But in general, you may have problems that don't have that, and you can build your own naive Bayes classifier. And I encourage you to try that if you have problems of this type that have these mixed forms of features. Naive Bayes provides a framework to do that. You have to write your own software for it, but it's not a very complicated thing to do. Okay, let's look at the naive Bayes for the Gaussian first. So again, the setup for the problem is that we have K classes. These are the labels. For instance, admit, deny, or waitlist. We have features, some P features. And these features, if they're Gaussians, could be test scores, a variety of different test scores on GREs and GPA and this kind of thing. And then we've got each of those scores put into a data matrix X. And each one of those student applicants then represents the 1 to n here. So each xi is an individual student applicant with those scores. We're interested in the likelihood, which is the f of x given gi for each one of the categories. Again, admit, waitlist, deny, for example. If we assume that those have a Gaussian distribution, it looks like this. If we assume it's a multivariate Gaussian, then we have that variance-covariance matrix to estimate. But in a naive Bayes approach, we're going to assume that they're all univariate Gaussians, so we don't have to do that. So each one then represents its own little individual Gaussian. And in this case, the second subscript in the mu and the second subscript in the sigma represents the class label. So if it's from the admit class, this would be, for instance, the Gaussian distribution associated with, let's say, a GRE math score for the admitted students. And they would have a mean for those students and a standard deviation for those students. Okay, so our rule then is we're going to pick among all the possible class labels given the data. If we have this likelihood ratio, as we've seen in our results for Bayes optimality, if the likelihood ratio favors, in this case, category I over all other categories, given the ratio of the likelihood versus the ratio of the priors. And now, again, we can write that because we have this naive Bayes assumption. It's just a product of Gaussians in the likelihood ratio. And that makes it very easy to calculate. And here's a picture of what it might look like. Again, considering two different classes. One class has a very broad distribution in the X1 feature, and a very tight distribution next to, and the other class is reversed. And you can see that the naive Bayes predictions, which are represented by that shaded area between the two, is a bit of a parabola. It's a nonlinear surface separating them. So it's not quite as extreme as what we saw in the quadratic, but it's not a linear surface as we saw in the linear discriminant function. It's a little bit of a compromise between the two. The nice thing about naive Bayes is we can do lots of different distributions with it. Here's a Bernoulli example. Again, you could think of our admission decisions, but now instead of having continuous features, we have 0, 1 features, for example. The rating of a recommendation letter, is it positive or negative, that kind of thing. So we could have a series of those features that we can incorporate here. And again, we've got K features, we've got, K classes, we've got P features of this type, of these Bernoulli type, and we have N applicants in this case, and that's the X1 through Xn, where each one of those is a vector with the scores for each one of those features. So our likelihood function then is represented again by a product. In this case, it's a product of binomials. And if you look, those thetas now are the probability, let's say, of getting a positive recommendation letter. So that would be, the I here would represent each of the class labels. So for example, it'd be the probability of a positive recommendation letter given this was an admitted student. And then we'd have a similar set of these for the ones who were denied and waitlisted. Okay, but this is just applying the binomial distribution, given that each one of these individual features is Bernoulli. Okay, we're going to choose again based upon the likelihood ratio. So we're going to pick the class that performs the best in terms of the likelihood ratio. Again, this is what we've seen now several times. The only difference now is we've replaced the likelihood where we saw before Gaussians. Now we have a product of Bernoulli's. A product of binomials. And that product of binomials then represents the likelihood. The ratio of those gives us the value we need in order to make our choice. Let's look at an example of how we could use this, this particular idea of binomial, product of binomials as the naive Bayes approach. And this is a common, naive Bayes is often used for text classification, and that's why we're going to look at this example. And it's done quite well there. Suppose we have a corpus of documents. We'll represent that by script D. So these are some documents, and we want to classify them into labels. Some examples of these could be, that are often used, we can have a corpus of reviews, and we'd like to say whether these reviews, let's say they're hotel or restaurant reviews, whether they're positive, neutral, or negative. It can also be email, for example, and we're trying to decide whether it's ham, which is good email, or spam, obviously not good email. We use a bag of word approach, so we're not going to consider the ordering of the words in any way. We're just going to take all the words in each one of the reviews or the emails and throw them into a set, and that's what we're going to look at. So script W is the vocabulary. It's all the possible words that could be chosen. WJ are the words in document J. So this comes from the individual documents. So when we look at one review, that's the words that are in that review, for instance. Okay, again, over and over again, we've seen the Bayes optimal classifier defined, and it's defined as the highest value for the posterior distribution. So, for example, in our review case, we would say it's a positive review if the positive review scored the highest in terms of its posterior distribution, its posterior probability. And that's all we're saying here, except, of course, we've rewritten it using Bayes' rule in terms of the likelihood of those particular words in the document given the class. So given a positive review class. And then that's times the prior as well, the prior of that class. Well, if we use this idea of naive Bayes, then each one of those words is going to have its own individual probability associated with it that we can use, its own probability distribution associated with it that we can use in order to create the likelihood function. So we can just write it then as shown. So this basically says that for each word that we see in a document, in a review, for instance, and that's then the likelihood of all the words in that document. Okay, given, for instance, a positive review, given whatever class label is on that particular that we're interested in seeing. So positive, neutral, negative, for example. So given a positive review times the prior probability of a positive review. Well, we can find the first term there, okay, which is the conditional probability, again, the likelihood of seeing a particular word. So, for instance, the word could be good or bad. It's the number of times we see the word good in a review that is positive. The number of times we see bad in a review that is positive. Over the summation of all of those, which is basically the summation of all the words that are within that corpus. Okay, a word WJ associated with a class may not appear in the training set. This is particularly important. So, for example, it could be that there's an unusual word or word that people might use rarely, but it does occasionally appear. And the problem is that if it doesn't appear in the training set, then it's going to get a likelihood of 0, which is not something we want. So let's say they have an unusual way of saying that this is a good or bad place. They could say that it's gone to the dogs or something like that. Not something that we would see often, dogs associated with a review, but maybe it is something that appears occasionally, and it may not appear in our training set. So we don't want to have something like that, show up, and it'll grossly affect the way the naive Bayes classifier works. And the way we get around that is by adding a smoothing parameter, which is alpha. And basically this says that any word that we have in our vocabulary is going to get some positive probability of being associated with one of the class labels. And that alpha could be relatively small, on the order of 0.01 or 0.001 or something. It could be a relatively small value, but it's just a way to keep the naive Bayes classifier from collapsing. So it's always, you have to include, if you're going to use this for text, you have to include that kind of smoothing parameter. And it's a very simple thing to do. You just incorporate it, as you can see, in both the numerator and the denominators. Okay, after you've got your training corpus of restaurant reviews, let's say, and we'll call that D of T, with some labels, positive, neutral, negative. Okay, so we need priors. Priors are really easy to get for these particular cases. It's just the number of positive reviews we see, for instance, out of all the reviews, or the number of negative reviews we see out of all the reviews. That's all we have to do is just count that number. And that's all this is saying. The number of reviews in that class, the number of documents or reviews in that class over the total number of documents or reviews that we have. All right, so let's look again at this likelihood idea. So we'll let the script WDC be the words, all the words in a document, okay, in the particular document that we have. So this is a review that we've gotten, and these are all the words that are in that review. All right. And this, again, this is a review that's come out of all the reviews that we've obtained. So the script W sub DC is the words that are in that particular review. And we'll let V be the total number of words in that review. Okay, so then when we look then at the likelihood for that particular word given that particular class, so seeing this word, say good, given a positive review, then all we do is we count the number of times we see the word good in that review, again with a little smoothing parameter, over the sum of all the words within that document, again with the smoothing parameters, and now that smoothing parameter is times the total number of words in the review. And here's an example of it, a made-up example. So we've got positive, neutral, and negative, and we're just counting the number of times we see something. So for example, if you look at the word horrible, it appears in none of the positive reviews, it appears in 2 of the neutral reviews, and it appears in 883 of the negative reviews. The word good appears in 2,183 positive, 729 neutral, and 691 negative reviews. And if you look at the word, by the way, the word horrible is an example of a word that has 0 appearance in positive reviews, but it could appear there. They could be saying, since we're just using a bag of words approach, this restaurant was not horrible, for example, and we wouldn't pick that up at all because, in fact, if we don't have that smoothing parameter, we'd lose that. Same thing with the word calamari. It's got 0. It appears very rarely, so this must not be seafood restaurants, but it's appearing very rarely, and that's something else we wouldn't pick up on. Finally, for this problem, we'll set alpha equal to 1.5, which is a good smoothing parameter to use for this small problem. Again, these are just things that we've created for this particular example, and you can modify it in your own example. When we apply the results, then, this is showing you the likelihood for each of those features. And the features in this case are each one of the words. So the likelihood of the word tasty appearing given a positive review, 8.8 times 10 to the minus 3. 3.35 times 10 to the minus 4 for a neutral review, and so forth. So we just multiply all of those together, and we multiply them times the priors. And you can see in this case we considered the reviews to be equally likely. It could be equally likely to be positive, neutral, or negative. And the result of doing that simple, the simple setup multiplication gives us the posterior distributions, which is shown, the highest of the posterior distributions. And we also took a log of it because these numbers get extraordinarily small. That's the thing about naive Bayes. This multiplication makes these numbers very, very small. So it's typical that we work with a log. And it makes it very clear that the positive review, that this is likely to be a positive review. And when you read it, I like the tasty calamari. That seems to be a positive review. So it's not surprising that that came out the way it did.